Welcome to my first ever attempt at a homemade recording for Clear Lake High School Honors Chemistry class. And what we're looking at today are energy changes in reactions. And remember that energy changes come about in chemical reactions because chemical bonds break and new chemical bonds form during the rearrangement of materials. So breaking chemical bonds means energy must be put in. Forming chemical bonds releases energy. So there are always energy changes in reactions. They tend to be either hot or cold. So the first concept that we're going to look at is what is called heat of reaction. Now if you would please write anything that shows up on the screen unless I say otherwise. So heat of reaction is defined as the energy that is produced or absorbed during a reaction. And there's an equation for the energy or heat of reaction where the equation is delta H, or heat of reaction, equals the enthalpy of the products minus the enthalpy of the reactants. Now, the heat of reaction really breaks down to mean change in enthalpy, and pronounced delta H. And so it's describing the change that takes place in the total energy during the reaction. The units for this would be usually in either kilocalories or kilojoules per mole of chemical that reacts. So we classify chemical reactions by the fact of whether they either absorb or give up energy during a chemical reaction. So an endothermic reaction is one in which energy is absorbed as the reaction takes place. So if we were looking at the delta H, the heat of reaction for an endothermic reaction, if energy is absorbed, that means that the products have more energy than the reactants. The reactants start off with a little bit of energy, they take energy in. And so when we use the equation that the heat of reaction equals the products, a big number, minus the reactants, a small number, we end up with a positive value for an endothermic reaction. That means that it's taking energy in as the reaction occurs. Now we're going to look at an example of an endothermic reaction. Let's take the example of baking soda. This is something that takes place when you cook. Baking soda is chemically sodium bicarbonate, NaHCO3, an ionic crystal. That's a 3. And you add energy to that, and I looked that up, it's 129 kilojoules per mole. We'll just put in the kilojoules. And then it turns into sodium carbonate, Na2CO3. Notice the H has disappeared. It produces water as steam and CO2 gas. And so the significance of that in cooking is that CO2 gas then is what causes the baked goods, the cake, or whatever it is, to rise. The point I want to make on this is that the 129 kilojoules, which of course is the energy, is on the reactant side of the equation. And remember, things on this side of the equation are things that are put in to the reaction. So the fact that energy is absorbed means that it has a positive heat of reaction, or change in enthalpy, and that we write the energy in on the left-hand side of the equation. Okay, so now let's look at an energy graph for this reaction and see what happens as the reaction occurs. So the sodium carbonate begins, these are the reactants, with a small amount of energy, NaHCO3. I may have messed that up on the previous page. And then the energy increases during the reaction. So here's the enthalpy, energy and enthalpy. I'll kind of use those interchangeably. It starts off low and finishes high. So here now are our products after the reaction, the Na2CO3, the water, and the CO2. And by another little thing that occurs is that the energy change never directly goes from the beginning to the end, but there's always a little bump in the middle that has to be reached for the reaction to occur. So now we know from our previous page that this amount of energy that was absorbed, I'll just extend that out so we can see it, from the beginning of the reaction to the end is our heat of reaction. And in this particular case, that was 129 kilojoules of energy. And it's a positive increase. We started with a little bit and we finished with a lot. And so that's an increase in the enthalpy. Now, this amount of energy that it takes to go from the beginning, from the reactants, let me change that color here, to the peak of this graph. It's the energy it takes to start the reaction. This is called activation energy, and the symbol for that is the energy symbol sub ACT for activation energy. And the activation energy is the energy required to start the reaction. You can kind of compare that to riding a what do you call those things? Roller coaster, where you start off at the beginning and the first hill has to go way up to the top before the ride will continue. Well, in a chemical reaction, the chemicals have to be lifted up to this state of energy in order for the reaction to occur. So that's the characteristics of an endothermic reaction. Okay, let's take a look at the other type of reaction, the opposite, which we classify as exothermic. And by far, more reactions are exothermic than endothermic. You think of all the things that burn and release energy, usually in the form of heat. So the first thing we can say about this is, since we start off with a lot of energy, and energy is released during the course of the reaction, the change in energy, or enthalpy, the heat of reaction, decreases during the reaction. It starts off with lots of enthalpy and ends up with little. So the change in enthalpy is a negative value. The more negative it is, the more energy is released. And in general, of course, because they're releasing energy, they feel warm or even hot to the touch, because that energy then goes out and warms up the environment or our hand, if that's what we're hanging on to the test tube with, whatever it might be. So combustion reactions of fuels and things, those are exothermic reactions, literally out, exothermic heat. Endothermic would mean, taking in heat. So we're going to look at an example of this as a combustion reaction. Let's take the reaction between methane, CH4, and since it's a combustion reaction, we need oxygen. We know that we have to get the reaction started with the addition of some heat. And of course, we know that it produces carbon dioxide and water if it's complete combustion. Let's see, to balance this, it doesn't have to be doubled. I think I just need a 2 here and a 2 here to make 4 oxygens. 2 plus 2 is 4, and 4 hydrogens we have there, and 1 carbon, so everything is good. Since this reaction releases energy now, we put the energy on the right-hand side, and this is a very exothermic reaction, releasing 890 kilojoules per mole. So that's why it's such a good fuel. It's a very exothermic reaction. Okay, now let's take a look at the energy graph for this reaction. So if you would sketch this graph, please. Again, we've got the enthalpy over here and the reaction occurring along on the x-axis. So now, since this is a hot reaction, let's do it in red. We start off this time with the fuel possessing a lot of energy. So this is the methane, and the oxygen. Now, it still takes energy to start the reaction, right? This won't burn without us first lighting it with a match. So it still has some activation energy. But now, once the reaction starts, the energy released is much larger than the energy that was put in. So we put a little bit of energy in here to start the reaction, and then we get a lot of energy back out when the reaction occurs. And so our products now, the H2O and the CO2, have very little energy left in them. And so on our reaction here, now we start off with this amount of energy, we finish with this amount here at the end, and so our delta H now is a negative number because it's decreasing. I should have made that probably even a bigger drop off, because that's supposed to be 890 kilojoules in this case. We still have our activation energy from the beginning up to the top. The energy required to get the reaction going in the first place has to meet some minimum value. So there's our activation energy shown by that arrow there. So is the effect of a catalyst on a chemical reaction. And a catalyst is a chemical which speeds up a reaction, but isn't itself part of the reaction. So I'll give you an example here. So it's a chemical that speeds up a reaction, but it's not one of the reactants or products. So we have a equation here showing the decomposition of peroxide, same peroxide that you buy in the store, which, as you can tell, is an endothermic reaction. I didn't find the exact amount of energy that it required, but it does take in energy. And since the energy is on the left in the equation, that's an endothermic reaction. And then it breaks it down into water and oxygen gas. And this reaction occurs very slowly. Usually the energy here is in the form of light energy, which explains why peroxide is sold in dark bottles, so it doesn't break down like this. But a catalyst for this reaction is yeast. And we put the catalyst over the arrow because, again, it's not a reactant, it's not a product, but it stimulates this reaction and makes it occur faster. And so if we take our energy graph now for this reaction, because it's endothermic, I'm going to start down here. We're going to put the activation energy in, and then it'll drop down but higher than it started. And so we have here our heat of reaction, change in enthalpy, delta H. Again, I can't give you an exact number on that, but there it is. And we have our activation energy necessary to get the reaction started. And so the way that a catalyst operates, the way that it speeds up the reaction, is that it lowers this amount of energy that it takes to start the reaction. It doesn't affect the total energy change in the reaction. The chemicals, the peroxide here, which I guess I could write on in here, and the water here and oxygen still have the same enthalpy that they would have had without the catalyst. What the catalyst does is allows that reaction to occur with less required activation energy. So the effect of the catalyst is to lower the activation energy to the point where the reaction can occur more rapidly. And so let's kind of summarize here. A catalyst is a chemical which speeds up a reaction, does not affect, hard to write with this thing, does not affect the heat of reaction, but it rather reduces the activation energy to make that occur. Okay, so what we're studying here is what's called thermochemistry, or the chemistry of heat and energy, and all chemical reactions involve changes in energy. All right, so I finally made it through after many trials of this, and I'll talk to you tomorrow.